Okay, hello, welcome once again to AMT 151 Basic Electricity. We are in week 5 of lecture. Can you guys please type in the chat if you can hear me? Before I get started too much, I want to make sure you guys can hear me. And as usual, if you guys need anything repeated or need to see a slide again, just type in the chat. Okay, good. Okay, so getting into week 5. Today we're going to talk about characteristics of magnetism. And then these numbers here are the page numbers from your 8083. I thought I'd put those on there so that if you guys want to follow along with reading or review later, you know where my material's coming from. So characteristics of magnetism in your AMT handbook 8083 is going to be on page 12-8. We're going to go through just a very, very brief introduction of electromagnetic induction. That is covered more in depth when you guys are taking your NDT class, non-destructive testing, but there is a lot of information about that on page 1212. We'll talk about some common schematics and symbols, or schematic symbols. There's a lot of information about that as well, including more in-depth information than what we're going to cover today. But we will continue covering that through the next few lectures, so pages 1224 through 1234. DC circuits with parallel resistors, page 1240, and some more discussion on capacitors, which is covered in the handbook on page 1251. Characteristics of magnetism. So magnets have properties that can attract certain metals, such as iron, steel, nickel, and cobalt. Magnetic vocabulary. So you'll hear things referred to as ferrous metals, non-ferrous, diamagnetic, and non-magnetic. There's also paramagnetic, but we don't deal with that too much. So ferrous metals. Ferrous metals are composed of iron or iron alloys. These can be things such as iron, steel, and nickel. There's other examples, but those are just a few. Non-ferrous metals. These are metals that do not contain iron. So any metal that does not contain iron is a non-ferrous metal. Diamagnetic. This is generally thought of as a non-magnetic material. This can include things such as water and wood, or other organic compounds such as petroleum, plastic. Copper is diamagnetic, generally thought of as non-magnetic. And then we have non-magnetic materials. Materials with no magnetic attraction and also cannot be magnetized themselves. So we have things such as water, rubber. These have no magnetic attraction to magnets, and water and rubber itself cannot be magnetized. I want to show you guys this chart because it has a good description of all of this vocabulary. So here you see it has a list of properties, and then also across the top we're talking about ferromagnetic materials, paramagnetic materials, and diamagnetic materials. So the state that you will find these in, ferromagnetic materials, which are materials that include iron. Remember, ferrous materials include iron, non-ferrous do not include iron or iron alloys. So ferromagnetic materials would be in a solid state of matter. Paramagnetic and diamagnetic you will find in solid, liquid, or gas. Ferromagnetic effect of a magnet. Ferromagnetic materials are strongly attracted by a magnet. Paramagnetic and diamagnetic are both, paramagnetic is weakly attracted to a magnet and diamagnetic is weakly repelled by a magnet. Okay, so then we also have ferromagnetic materials behavior under non-uniform field. So under a non-uniform magnetic field, ferromagnetic materials tend to move from low to high field regions. If you don't understand what I mean by that, there's some reading in your text that explains that further. Paramagnetic materials behavior under non-uniform magnetic field tend to move from low to high field regions. So same as ferromagnetic. And then diamagnetic behavior tend to move from high to low regions in a non-uniform magnetic field. So that is a description of the behavior of those different descriptions of materials. We have ferromagnetic materials effective temperature. So the effective temperature above Curie point, it becomes a paramagnetic, which that's not really, it's a little bit beyond the scope of this class, but I just want you guys can refer to this chart to learn a little bit more about these materials and their vocabulary. So paramagnetic materials effect of temperature, with the rise of temperature, it becomes a diamagnetic. And then diamagnetic has no effect when there is either an increase or a decrease in temperature. Permeability is something that we need to know, especially as AMT mechanics. Permeability has a big deal to do with our instruments, so that magnetic fields don't interfere with our instruments, and we want to surround our instruments with material that has a high permeability, so that magnetic field will be attracted to the material surrounding the magnetic instrument rather than the instrument itself. So ferromagnetic materials permeability is very high. Paramagnetic materials permeability is a little greater than unity. And diamagnetic materials permeability is less than unity. And then you also have susceptibility and some examples, which we covered in the slide. Ferromagnetic materials, iron, nickel, cobalt. Paramagnetic materials would be lithium, tantalum, and magnesium. And diamagnetic materials, like I said, copper, silver, and gold are also diamagnetic, basically considered non-magnetic. Okay, and that was some vocabulary that would be good for you guys to know, especially for your ASA testing. There aren't very many questions on magnetism and properties in your ASA test guides, but there will be more questions on that when you get to the non-destructive testing portion of questions in this entire course. So moving on to magnetic flux. What is magnetic flux? Also referred to as lines of force. Here you have a picture of a bar magnet, and these are all iron filings that have been laid around that magnet, and this is a practice used to see where the lines of flux are in this magnetic field. In this specific picture, these are the lines of flux of the bar magnet. So you can see that there is a concentrated flux out here at the ends of the magnet, which is the poles. And then there's also lines of flux circulating from the middle of the magnet. So using iron fillings, we can find the shape of a magnetic field. A magnetic field is more concentrated at the ends of the magnet, which are the poles. Magnetic permeability. Magnetic flux has no known insulators since they can pass through all and any types of material. So magnetic flux, or the lines of force in magnets, can pass through any material that we know of. There's no material that can contain all of magnets' lines of force. But magnet lines of flux can pass through some materials easier than others. These materials that it can pass through easier than others, we use to shield magnetic instruments. Materials such as soft iron. Soft iron offers little opposition to magnetic flux and guides away from the instrument. So same reason that, oh, well, actually, you guys aren't in my instruments class, but in the instruments class right now, we're working on magnetic compass swing. So same reason why we want to use a brass screwdriver if we need to make any corrections, because we want to direct those the magnetic flux away from the instrument. Okay, and now we'll talk about electromagnetic induction just briefly. Electromagnetic induction is the production of an electromagnetic force, or EMF, which also is known as voltage, across an electrical conductor in a changing magnetic field. Electromagnets, what are they? Electromagnets are a type of magnet in which a magnetic field is produced by an electric current. We use electromagnets in certain components, such as electrical instruments, motors, generators, relays, solenoids. These components all can use electromagnets because they can use that production of an electrical current through these electromagnets. Okay, schematic symbols. So that was our brief overview of electromagnetic induction. We really, for this class, don't need to know much more than that. You just need to know what the uses are for electromagnets and electromagnetic induction, and what it is. Schematic symbols. So today we're going to talk about a few schematic symbols. This is by no means all of them. We will just talk about their symbol and what they are, what the name is, so that when you guys are looking at schematics in lab, you can understand all of what probably Mr. Kimball's going to be asking you. So we have a few slides today of symbols, and then we'll continue going over circuit diagram symbols and get into some circuit diagrams and tracing the diagrams as we move along. Okay, so the most basic part of a schematic is our wire. So that's our first one listed here, and it's just going to be a thin black line most of the time. I've never really seen it as anything else. Sometimes you have a dotted line to represent if there's another wire running near a wire or a conductor, or if there's a wire running behind it, something like that. But so our wire line, we have our conductors, we have our connected conductors. So you can see that they're attached here in different ways. Not connected conductors, so this means that these are running past each other but not connecting to one another. We have our ground, a cell, our battery, can be either one of these. You guys have probably seen that before, and I've drawn it on the board before. Here we have an incandescent lamp. That's our symbol for an incandescent lamp. Our fuse. We have our resistors, which we've talked about a lot. So we have our fixed resistors, which we've used in some calculations, variable resistors, which that's our potentiometer symbol, and our rheostat symbol. We have our switch. Do you guys know, is this switch in the on or off position? Go ahead and type in the chat. And then we have our voltmeter and our ammeter. You guys will be seeing a lot of that, especially as we start getting towards your tests. I don't know what Mr. Kimball's using in lab as far as schematics so much, but you might see some of that in lab. Yes, I see a couple responses. The switch is in the off position. So if this arm if the switch was in the on position, this arm would be pushed down to kind of make one straight line. And these are the switch points of contact in schematic form. I see that Tran asked, what does a rheostat? Let me see if I can see this whole question. What does rheostat use for? So that is a good question, and that was also covered in one of your previous lectures. Does anybody remember what a rheostat is used for? What the purpose of a rheostat is? I believe, actually, the rheostat information is in the lecture when I was having trouble with the internet. Yeah, so Mr. Malone says it can limit current. That's exactly what we use it for. Current limiters. It's another type of a variable potentiometer. So make sure you go back and review slides from the previous lecture. I did mention a rheostat, and I don't think it was the lecture on Wednesday, but I think it was last Monday's lecture. There was a little bit of information about that. Okay, so moving on to some more symbols, we have ground again, ohms, which we all know is for resistance, our fixed resistor. Here's a couple of different types of switches. So the one that we had on the previous slide was our toggle switch, and this one is also in the off position. You have a push-pull switch, which sometimes you'll see in a circuit breaker diagram. So this push-pull switch is also in the off position. If we wanted to show it as on, then this would just be, how do I say that? This would just be pushed down to make one straight line, also with this 90-degree line. But that's symbolizing that the circuit is actuated and working. And then same thing with a push button circuit. So push button circuit would be, you know, like an elevator button, like you're just going up and pushing it. Push pull circuit would be you can push it in, and you can also pull it out the other direction. Okay, so that's the difference between those, or a couple different schematic drawings for switches. We have our one-way diode, and diodes, I think we get into an advanced electricity, or at least more in depth. Our one-way diodes, Zener diodes, transistors. Remember, we had transistors that were positive and negative. Those I know, PMP type and this stuff I know we get into in advanced electricity. Again, our wires crossed or not connected. Capacitors. So we have capacitor symbols. I most always see this first one in our schematics, at least as far as it goes for this class. So I don't ever really see these two symbols in schematics that we're using in this class at OCC. Here we have our circuit breakers. Okay, some symbols for circuit breakers. Another variable resistor symbol. So this was actually our rheostat symbol, which rheostat is a variable resistor, so it's just giving you another example of, that's just a general term, variable resistor. Coil, if we have a coil in our schematic. Spark gap, that's not something that you'll see, at least not in this class, okay? Motor, you will see the schematic symbol for motor. Contact points, you will see that. Silicone controlled rectifier. You might see that symbol in some of our schematics, but it's not really something that we're going to be talking a lot about in this class. And again, wires crossed or connected versus wires crossed but not connected. Okay. And some more symbols. I think most of them we probably already went through. We have, I wanted you guys to see, we have a coil here. And we have two different types. This is our inductor coil, and this would be our symbol for an inductor solenoid, okay? So depending on what schematic you're looking at and what component, electrical component it has, you'll see some of those different symbols. Ground, another symbol for battery. And again, connection and terminal with our wires. Our switch is open. Our circuit breaker. Crossover of wires. You will see this symbol, direction of current, but it's not to be confused with the diode symbol. So here you see the diode, one-way diode, and Zener diode. So if a schematic is showing you the direction of current, you're just going to have this arrow. The diode has this line in front of it, and then the Zener diode has this line and this like 90-degree angle as well. Okay, and a lot of schematics do show the direction of current when you're looking at them so that you can use that in your calculations or just kind of know which way the schematic is operating. A capacitor, again, I will most often see that symbol. And again, variable resistance, variable resistor. Okay, so that is just a few. those diagrams. That's just a few of the schematic symbols that you guys will begin seeing. I'm not quite sure where you're at in lab, but you might see them already. You'll be measuring some things with your voltmeters and ammeters and ohm meters, and you'll want to place them in certain, you'll have a schematic that will ask you, place your voltmeter here, and it will give you a schematic showing you this symbol across a circuit. And so you will see that. You will see your incandescent lamp, fuses, you'll see that. So okay, so it's just a little bit of information. Like I said, we'll continue we'll be doing kind of a little bit, we'll advance on those symbols and have more symbols to review, and then begin reading some simple circuits, tracing some circuit diagrams, and then we'll move on. We'll just keep building on that knowledge with the schematics and stuff like that. So DC and parallel circuits. So I think we've talked a lot about series circuits, and series circuits are pretty easy. It's pretty much just a lot of addition and basic division. So parallel circuits are a little more advanced, and then later we'll also talk about parallel and series circuits together. So this is a good video with a description of and some examples of DC circuits with parallel resistors. So last lecture we went over total resistance and how to calculate total resistance, and also how to calculate power. So this will be kind of adding some more into that. We're going to see how to begin to calculate parallel circuits with resistors, the total circuit. So that means, power, current, total resistance, which we learned about last time.
When Congressman Harley Ruda wrote a bill to stop federal funding from going to China-owned companies, most Democrats didn't like it. So Congressman Ruda worked with Republicans and made it a law. Harley Ruda, country over party.
This video is all about how to solve DC circuits with parallel resistors. So consider the circuit shown below. The current flow of each resistor. Let's call this resistor 1. How do we determine how much current flows through the resistor? Well, we can use Ohm's law. We use AMT. So the voltage of the battery, which is the voltage across each resistor, that's going to equal the current through the resistor times the resistor itself. So to calculate the current, it's going to be the voltage divided by that particular resistor. So we have 12 volts across this resistor. Divided by 4 ohms, that's going to give us a current of 3 amps flowing through that resistor. So that's I1. Now to calculate I2, it's going to be the voltage of the battery divided by R2, which is 6 ohms. So the current flowing through this resistor is 2 amps. 12 divided by 6 is 2. Now how much current is delivered by the battery? Now keep in mind there's 2 amps of current flowing in this section of the wire. The current released by the battery is the sum of the currents flowing through each resistor. The current that flows through this segment has to be 5 amps. It makes sense because at this junction, 2 went to the right and 3 amps went below. So the 2 amp current flows through this portion of the wire, and it meets up with the 3 amp current, where it turns to the battery with a current of 5 amps. Now let's move on to part C. How much power is absorbed by each resistor? So let's start with resistor 1. To calculate the power, you can use this formula. It's going to be I1 squared times R1. So there's a current of 3 amps flowing through that resistor. Resistance is 4 ohms. So 3 squared is 9 times 4. is 36. So 36 watts of power is consumed by R1. Now let's focus on R2. Now, another equation I'm going to use is V squared divided by 1. In a parallel circuit, the voltage of each resistor is the same. It's equal to the voltage of the battery. So we have 12 volts across that resistor, and then we're going to divide it by R2, which is 6 ohms. So 12 divided by 6 is 2, and 2 times the other 12 is 24. So 24 watts.
The DSCC is the only committee solely dedicated to flipping the Senate. And right now, that's the only way.
Is used up by this resistor. Now let's calculate the power delivered by the battery. So we're going to use this equation, voltage times current. The battery is 12 volts and it delivers a current of 5 amps. So 12 times 5 is 60 watts. Now as you can see, notice that the power delivered by the battery, which is 60, is equal to the total power absorbed by all the resistors. 36 plus 24 is 60. It has to be balanced. Due to the law of conservation of energy, the rate at which energy is transferred from the battery is equal to the rate at which the resistors absorb that energy. Now let's move on to the last part. Calculate the total resistance in the circuit. Now there's two ways in which we can do that. The first way is to take the voltage of the battery and divide by the total current in the circuit. So we have a 12-volt battery, and 5 amps of current is the total current in the circuit. So it's going to be 12 divided by 5. And so the equivalent resistance of this circuit is 2.4 ohms. Now we can use the formula to confirm this answer. And for a parallel circuit, 1 over RT is equal to 1 over R1 plus 1 over R2. So if you raise both sides to the minus 1, total resistance becomes this, 1 over R1 plus 1 over R2 raised to the negative 1 power. So R1 is 4 and R2 is 6. 1/4 plus 1 over 6, that's 5 over 12. And if you raise that to the minus 1, you get 12 over 5, which is 2.4 ohms. So this will give you the same answer. So now you have two ways in which you can calculate the total resistance of a parallel circuit. Now let's work on a similar example, but with 3 resistors. And we're going to answer the same questions. So you can try this problem if you want to. So we're going to say that this is a 3 ohm resistor. This is going to be a 4 ohm resistor. And here we're going to have an 8 ohm resistor. We're going to use a 24 volt battery. So go ahead and calculate the current in each resistor. Let's call this R1, R2, So to calculate I1, it's going to be the voltage of the battery divided by R1. So that's going to be 24 volts. By 3 ohms. So that's going to be 8 amps of current that flows through this resistor. Now to calculate I2, it's going to be the voltage divided by R2. So it's the 24 volt battery divided by the 4 ohm resistor. So the current that flows through this segment is 6 amps. Now for I3, we're going to do the same thing. It's going to be V divided by R3. So 24 volts divided by 8 ohms. And so I3 is equal to 3 amps. Now let's calculate the total current.
Tired of scrounging YouTube for math help? ThatTutorGuy.com has videos covering everything from pre-algebra to calculus, chemistry.
Total current in the circuit is going to be I1 plus I2 plus I3 based on Kirchhoff's current law. So if we add 8 plus 6 plus 3. 8 plus 6 is 14. 14 plus 3 is 17. So 17 amps of current leaves the battery. Now, according to Kirchhoff's current law, the current that enters this junction equals the current that leaves the junction. So we have 17 amps that's entering, 17 amps must leave it. So notice that 8 amps went down this way. That means the other 9 amps has to flow through this part of the wire. Now once we reach this junction, 9 amps enters in, 6 amps flows in the downward direction, so 3 amps this way. And then 3 amps flows this way. And then at this point, 3 amp current meets up with the 6 amp current. And so 9 amps is going to be flowing in this wire. And then the 9 amp current meets up with the 8 amp current. And so 17 amps flows back to the battery. And so hopefully this gives you a good visual illustration of how the current flow works in a circuit. Now let's move on to part D. How much power is delivered by the battery? And also part C. How much power is absorbed by each resistor? So to calculate the power absorbed by the first resistor, we can use I1 squared times R1. So we have 8 amps of current flowing through that resistor. The resistance is 3 ohms. So 8 squared is 64 times 3. That's 192 volts. Now let's move on to the second resistor. So I'm going to use V squared divided by R. So the voltage across every resistor in a parallel circuit is going to be the same, 24 volts. And resistance is 4 ohms. 24 squared is 576 divided by 4. So that means that 144 watts of power is consumed by the second resistor. Now for the last one. So P3 is going to be, we use voltage times current. There's 12 volts across it. The current that flows through it is 3 amps. So then 24 times 3, that's 72 watts. So now let's calculate the power delivered by the battery. It's voltage times current. So it's going to be 24 volts multiplied by 17 amps. And so the battery delivers 408 watts. So if we add 192 plus 144 plus 72, it adds up to 408, which means everything so far is correct. Now, just like before, we're going to calculate the total resistance. Using this equation, it's voltage divided by the total current. So the voltage of the battery is 24 volts, and the total current is 17 amps. So the total resistance is much less than each individual resistor. The lowest resistance is 3 ohms. Every time you add a resistor in a parallel circuit, the total resistance decreases. In a series circuit, every time you add a new resistor, the total resistance increases. So if we take 24 and divide it by 17, you'll get an equivalent resistance of 1.41 ohms. Now let's get the same answer using this one. So it's going to be 1 divided by R1 plus 1 over R2 plus 1 over R3 raised to the negative 1. So it's 1 over 3 plus 1 over 4 plus 1 over 8. And this will give the same answer of 1.41 ohms.
Brush your teeth in less than 10 seconds with this revolutionary toothbrush. It was
Okay, let's see the video. So I hope that was helpful. Those videos have really good descriptions and examples. So refer to that if needed. Um, okay, I see a couple people here saying that there was some trouble with the video. You guys weren't hearing it correctly. I will post that link so that you guys can watch it on your own as well. That might have been me in the background just shuffling things around. Sometimes I notice that the sound on this picks up background sound a lot. So, it's already 5:12, so yeah, what I will do is I will post a link to that video, on Canvas so that you guys can watch it on your own, because it will definitely help you with the quiz, okay? And just as review, this was our formula last week when we were calculating total resistance in parallel circuits, and also our formula from calculating total resistance in series circuits. Here is another diagram that is a good way to follow, here's the battery, the current draw is going this way. In the video you saw, it talked about total current. It has left the battery, and when it crosses this resistor, it puts a load on that current, and there is a current draw across resistor 1. There's a formula for that if you want to find the voltage across resistor 1 and convert that to power. And then same thing with resistor 2, resistor 3. And on your way back, as seen in the video, you should be picking up all of those currents and get the total current, the current that went out of the battery goes back into the battery. So that's a good diagram for all of your formulas there to use. All of these formulas will be provided to you on your quizzes and exams. Anything that begins to get more complicated, those formulas will be provided to you. So you guys don't have to memorize any formulas, but you do need to know how to use them. Okay, and a little bit more discussion about capacitors and capacitance. We talked briefly about capacitors in the last lecture, and I just want to go over some more information. We did talk about capacitors and what they are. So I have a video here of capacitors in parallel and series circuits. Let me see how long that is. Yeah, I think we have time for that. So we will watch this.
In this video, we're going to talk about capacitors in series and parallel. We're going to go over some equations that you need to know, and we'll cause some problems. So let's say let's say the first capacitor has a value of 100 microfarads. The second capacitor has a value of 200 microfarads. What is the equivalent capacitance? For parallel circuits, the equivalent capacitance is simply the sum of all capacitors connected in parallel. So it's 100 plus 200 is 300 microfarads. And that's all you need to do to find the equivalent capacitance. Now, how much charge is stored in C1? To calculate the charge, Q1 is equal to C1 times V1. So you need to know the voltage across C1. In a parallel circuit, the voltage across every element that's parallel to one another is the same. C1 is connected directly across the battery, so it has a voltage of 10 volts when it's fully charged. And the same is true for C2. They will all have the same voltage. So V1 is 10 and V2 is 10. So now we can calculate Q1. So it's going to be C1, which is 100 microfarads, or 100 times 10 to the minus 6 micros 10 to the minus 6. And V1 is just 10. So Q1 is about 0.001 coulombs. That's the unit of electric charge. What about C2? What is the charge stored on C2? So we can use this equation. Q2 is equal to C2 times V2. So that's 200 times 10 to the minus 6 times 10 volts. So it's going to store twice the amount of charge compared to C1. So it's 0.002 coulombs. The total charge stored in this network is basically Q1 plus Q2. So it's 0.001 plus 0.002. So it's 0.003 coulombs. You can also find the total charge by taking the equivalent capacitance and multiplying it by the voltage. So 300 times 10 to the minus 6 multiplied by 10 will also give you 0.003. So that's another thing to do. Now, how can we calculate the energy stored in C1? What is the electric potential energy stored in that capacitor? One equation that you can use is this one. It's 1 half CV squared. So it's 1 half times 100 times 10 to the minus 6, that's capacitance, times the voltage across that capacitor, which is 10, and complete the square. So this is equal to 0.005 joules, which I'd say it's about 5 millijoules. Now what if we have a capacitor circuit in series? Let's use 3 capacitors instead of 2. So on the left we have a battery. Let's see 2 different sides of the battery. And let's say the battery's voltage is 50 volts. So call this capacitor C1, C2, and C3. Let's say C1 has a capacitance of, let's use large values. Let's say C1 is 2 farads. C2 is going to be 3 farads. And C3 is going to be 5 farads. Now typically most capacitors, they're in a range of microfarads. Supercapacitors have this much capacitance, but just intensity, we'll use these numbers. What is the equivalent capacitance in a circuit? That's the first thing we look for. A simple way to find the equivalent capacitance in a series circuit is going to be 1 over C1 plus 1 over C2 plus 1 over C3, all raised to minus 1. So it's 1 over 2 plus 1 over 3 plus 1 over 5. And just type this in exactly the way you see it in your calculator. So the equivalent capacitance is about 0.9677 farads. Now with this information, how can you find the voltage across each of the capacitors? Sometimes you may need to find the voltage of just one of the capacitors, and then with that you can find how much potential energy is stored in the capacitor. Let's focus on finding the voltage of each. So once you have the equivalent capacitance, the next thing you need to do is calculate the charge. Now, there's some differences you need to know between a series and parallel circuit for capacitors. In a parallel circuit, the voltage across each capacitor is the same. It's equal to the battery's voltage. In a series circuit, the voltages across each capacitor will be different if the capacitance is different. Now, in a series circuit, the charge stored on each capacitor is the same. In a parallel circuit, the voltage across each capacitor is the same, which you understand the difference. So once we find Q, this Q will be the same as Q1, Q2, Q3. They all equal each other. And this will be very helpful in calculating V1, V2, and V3. So let's find Q. It's equal to the equivalent capacitance times the total voltage, the voltage of the battery, which is 50 volts. So 0.9677 times 50, that's equal to, in my opinion, 48.39. So that's the total charge, which is the charge on each capacitor, which are the same. So now let's find V1. V1 is going to be Q1 So take the charge divided by the capacitance. Now if you have microfarads, make sure to add 10 to the -6 when dealing with your calculations. In this video, you just gotta divide by 2 since it's in farads. So 48.39 divided by 2 is about 24.2. That's the voltage across C1. Now to find the voltage across C2 is going to be Q2 divided by C2. Q1 and Q2, they're both equal to Q. So it's going to be 48.39 divided by 3. And then that is equal to 16. Now to find C3, it's going to be Q3 divided by C3. To find V3. So V3 is going to be 48.39 divided by 5. And that's about 9.7 volts. Now, let's clear up a few things. Notice that the total voltage is equal to V1 plus V2 plus V4. V1 is 24.2, V2 is 16.1, V3 is 9.7. So if you add these values, you should get 50 volts, which is equal to the voltage of the battery, That's how you know if your answer is correct. It has to agree with one another. The sum of these three values has to equal the battery's voltage. Now let's calculate the potential energy of C2. It's going to be 1/2 CV squared. Now that we have the voltage, we can find the potential energy. So capacitance is 3 farads. The voltage across it is 3.1. And so this is equal to 388.8 joules. So that's it for this video.
Good
Okay.
grammar.
So that's going to be it for lecture today. Don't worry too much about the capacitance calculations. We're going to continue going over those because they get a little more tricky than what we have been doing. So today there's not going to be any capacitance calculations on your quiz. There might be some questions regarding some of the information that you saw as far as capacitors and electrical circuits, but there won't be any calculation problems. There will, however, be calculation problems on your quiz for parallel circuits. So if you did not understand that video or could not understand it, I will post that link and make sure that you review it if you need to, okay? So I will see you guys Wednesday, and Mr. Kimball will see you in lab. Thank you. If you guys have any questions, you can stay around and type them in the chat. I will be on here for a few minutes while I post that link.